What if you dropped a bowling ball from space? Instinct says meteor, fireball, crater, dramatic slow-motion news footage. Wrong, mostly. The real answer is stranger, more technical, and honestly a little anticlimactic, which somehow makes it more interesting. Here's the first problem nobody thinks about. You can't just drop something from space. Space isn't a shelf. Anything up there isn't floating. It's falling sideways so fast it keeps missing the ground. That's what orbit actually is. A satellite in a typical low Earth orbit is moving at roughly 17,000 to 17,500 miles an hour. Not hovering, not resting, constantly falling and constantly missing. So to get our bowling ball to actually come down, you don't need to kill all that speed. That's called deorbiting, a relatively small retrograde burn that lowers its orbit until the atmosphere catches it. You don't need to cancel out 17,000 miles an hour in one dramatic maneuver. You just need to nudge the low point of the orbit down into thicker air. Let's say we manage it. Our bowling ball dips downward. But here's the key thing. It's still moving at several thousand miles an hour when it actually reaches the atmosphere. This isn't a gentle drop. It's still basically a very fast, very determined bowling ball. It gets complicated fast. As it plunges into the upper atmosphere, around 60 miles up, the air gradually becomes dense enough for serious drag and heating. And here's the part most people get completely wrong. It's not friction burning it up. At those speeds, the ball is moving faster than the air in front of it can get out of the way. So that air gets violently compressed into a shock layer just ahead of the surface. That compression, not rubbing, is what generates the extreme heat. The compressed air can become thousands of degrees hot, with parts of the flow becoming ionized into plasma. The ball isn't fighting friction, it's punching a hole through air that has nowhere to go. This is the point where the open loop from earlier gets answered. Does it survive? For a lot of objects, the answer is no. This is exactly what happens to a lot of space debris and meteoroids, a process called ablation, where the outer surface burns and flakes away layer by layer, shedding mass as it falls. Small, lightweight, or oddly shaped debris often doesn't make it. Loose panels, brittle fragments, thin sheets of material, these tend to burn up completely before reaching the lower atmosphere. But it's not an absolute rule. Survival depends heavily on mass, density, shape, and orientation as it falls. Which is exactly why bowling balls have a real shot. It's a compact, relatively massive sphere with no fragile components or thin panels to tear apart. That density matters enormously here, because ablation burns away surface material based on surface area, and a solid, dense sphere has comparatively less surface area to lose relative to its mass. It's the same reason a small, dense meteorite is more likely to survive reentry than a larger, more fragile chunk of icy comet debris. So there's a real chance our bowling ball, or at least a scorched, resized version of it, survives the trip down mostly intact. Here's where it gets stranger still. As it gets deeper into the atmosphere and loses velocity, the extreme heating gradually gives way to ordinary aerodynamic drag. The atmosphere thickens, drag increases, and it slows dramatically. By the time it's a few miles from the ground, it's not screaming down at orbital speed anymore. It could eventually settle toward a terminal velocity on the order of 150 to 200 miles an hour, depending on its final mass and how it tumbles. Now, here's the part that undercuts the whole meteor fantasy. That impact speed is fast, genuinely dangerous if it hits something, but the destructive picture people imagine doesn't quite hold up either. A bowling ball is roughly 50 times heavier than a baseball, so even at a comparable speed to something thrown hard, the kinetic energy on impact is far greater than a simple fastball comparison would suggest. No meteor-sized shockwave, no giant crater, no Hollywood fireball, but still a genuinely heavy, genuinely fast, slightly melted chunk of resin hitting the ground hard enough to do real damage to whatever's underneath it. This isn't hypothetical guesswork either. We have real-world case studies. Space debris survives re-entry and reaches the ground more often than people assume. Fragments of satellites, rocket stages, and even chunks of the Mir space station have been recovered on Earth's surface, scorched, pitted, sometimes barely recognizable, but intact enough enough to identify. Some meteorites survive as relatively small rocks, too, occasionally punching through roofs or damaging cars, arriving not as apocalyptic fireballs, but as unassuming rocks that get discovered days later by someone with a metal detector. So here's where we actually land. Getting a bowling ball to fall from space requires a relatively small nudge to start a descent, surviving a shock-heated environment hot enough to glow, then getting slowed back down by the same atmosphere that almost destroyed it in the first place, only to hit the ground carrying more force than most people would ever expect from something that started its journey just floating quietly in orbit. Space, it turns out, is far less dramatic and far more technical than the movies make it look. The universe doesn't do dramatic entrances. It does orbital mechanics, shock physics, and a whole lot of paperwork before anything actually falls. So here's the real question worth sitting with. If a dense, unremarkable object like a bowling ball can survive a trip through superheated, shock-compressed air and still hit the ground with serious force, what does that tell you about how much of danger from space comes down to an object's mass, shape, and speed, not just how dramatic it looks falling? We'll dig into that next time. For now, maybe just don't leave your bowling ball on the space station.